Okay, because it's easier to solve, because
If something can be explained simple, why not?
if I can, I should, right? If I have a fixed point, I should go look at it. I would be a little bit more pessimistic. It's the only thing we can actually do with any reliability in nonlinear systems is zoom into fixed points and linearize them. We know everything about linear systems, so we go find fixed points and we linearize about them. And often we try to control our systems to stay near those linear fixed points. Yeah?
You can go to the Liouville equation, and you have a linear equation for the probability.
We'll get there. Okay, so the basic idea, if I have this x dot equals ax, it's easy for me to write down the solution at all future times. Okay, that's really, really important. I don't have to simulate some really complicated nonlinear stiff ODE with some fancy time stepper. I can just step this forward to any time in the future. Scott Dawson pointed this out also, that my control problem becomes like a one-line Python command. That's awesome. Okay, I love easy solutions. And you've all seen this before, but I think this is just really fun. When I have a linear system like this, it's easy to change coordinates. And this is, the reason I'm pointing this out is not because you don't know about changing coordinates in linear systems, but I want to take a big step back and point out that changes of coordinates is probably our most powerful tool in analyzing any system. That's how we discovered F equals ma, is by taking us out of the Earth-centric coordinate and putting us in the sun-centric coordinate. Took 100 years or more, okay? But then you got F equals ma out of it. Relativity is a coordinate transformation. The Fourier transform is a coordinate transformation that makes our lives simpler, okay? And this is the one that you're most familiar with, is this one here. So that's why I'm talking about this, because dynamical systems is also about finding coordinates where things are simple. So in linear systems, it's easy to change coordinates into some z coordinates. This t is just a matrix. I know how to multiply matrices. And in z coordinates, my z dot equations transform like this. Okay, so my A dynamics just become t inverse AT. That's what the dynamics look like in the z coordinates. And so I can do things like I can try to design my transformation t so that my z dynamics are diagonal and decoupled. Wouldn't that be nice? Because then I could solve the z1 equation, the z2 equation completely separately, okay? And in fact, if you write down that lambda equals t inverse AT, you obtain the eigenvalue equation. This is how you should think about eigenvalues and eigenvectors. They are literally the coordinates that turn your linear system into a diagonal system. That's why they're useful. That's one of the main reasons they're useful, okay? And that's how you can think of the Fourier transform too. It's the exact same thing. Okay? And so now what you can do is you can write your state x at some future time t in this relatively simple formula that you've all seen before. But the reason I'm writing this up is to, again, bring it back to this idea of coordinate transformations. Eigenvectors of my matrix A define a coordinate system where my life becomes easier. That's what we want in all dynamical systems. And so the way I think about this equation, I break it down into these pieces. T inverse times x naught takes my initial condition and maps it into eigenvector coordinates. So now I'm in z naught. It's easy to advance my z dynamics because they're diagonal and decoupled. So I can advance z forward in time by just multiplying it times e to the diagonal matrix times t. And now I have z at some future time. I map back into my real spatial coordinates again through this eigenvector transform. So it's really nice interpretation of this in terms of coordinates. So linear systems are nice because it's easy for us to find good coordinates for them. Okay, and there's control analogs of this as well. Good. So I want to walk you through at least one example of linearizing something and doing a phase portrait. I think that's super important. This is the Duffing equation, and this is not the right order for the slide. My apologies. So this is the Duffing equation I had in the middle. So we've talked about linear systems. Now we're going to talk about how we can linearize around fixed points to build these phase portraits for nonlinear systems. This is the Duffing equation here. So x double dot equals x minus x cubed. And the way you can think about this is essentially a particle in a potential field, this v of x potential So my force is minus gradient of my potential. This is just Newton's second law. And this curve here is my potential. And the way I think about this dynamical system is if I had a bead or a marble and I dropped it in this potential, it would roll around. Yeah? And if I started it right here, it would just roll back and forth. And if I started it here, it would roll back and forth. And if I started it here, it would go around, and so on and so forth. No friction. Okay? So when you have a system like this, you can suspend its variables into a higher dimensional system of lower order. This is a second order system, so now I wrote it as a system of two first order differential equations. So x dot equals velocity, velocity dot equals all this stuff on the right-hand side. And now if you look at this, the system has three fixed points. V always has to be 0, but now x can either be 0, +1, or -1. Okay, those are all of my fixed points. And now what I can do is I can compute that linearization of this fully nonlinear system through this Jacobian here. Does everyone know how to compute a Jacobian? Anyone want me to tell you? It's just like partial of f1 with respect to x, partial of f1 with respect to v, f2 with respect to x, f2 with respect to v. And I evaluate this at these three fixed points. And what I find is that the plus and -1 fixed points, sorry, I should tell you what the axes of this are. This is x, and this is v, and this is my phase portrait. So what this tells you is that this fixed point is stable. It has eigenvalues that just go, plus and minus I omega. So if I start here, I just go back and forth in x and v, which are circles here. If I look at this fixed point, the 0, 0 fixed point, then I have a saddle point. I have plus and minus real eigenvalues. So one of them stable and the other one's unstable. And this makes sense because if I started my marble right on that hill and I pushed it to the right, it's going to go to the right. That means if I start my marble right here and I push it to the right, it goes in this loop. And if I push it to the left, it goes on this loop. And then if I have slightly more energy, the colors here denote how much energy I have in my marble, then I'll just go around in phase portrait. So this is a really useful thing that we can do even in very high dimensional nonlinear systems like fluids. So the reason I'm showing you all of this is because we're going to look at this exact same type of picture for fluid systems in a little bit. Okay. Now, I absolutely love saddle points. I think that they are so cool and so important, and I'll tell you a lot more about them. Saddle points are essentially fixed points where some of the directions are stable and some of the directions are unstable. Okay, so in some directions I'm coming into the fixed point, and in other directions I'm fleeing away from the fixed point. That's what you see here. The green arrows are pointing in, the red arrows are pointing out. This is a nonlinear system defined by this equation here. And so essentially in this kind of a fixed point, you have stable and unstable manifolds. This red curve here is ironically called a stable manifold, even though it is fleeing away. Because if you think about it, this green set of arrows is pulling material in towards that red curve. Material is being glommed on to this red curve. It's adhering, it's attracting onto this red curve, and then being carried away. So things attract onto the stable manifold, and they repel away from this unstable manifold because this red curve is carrying stuff away from the green manifold. Okay? Good? And in general, I like to think about saddle points as being areas where uncertainty gets magnified. Okay? So for example, if I have these balls of uncertainty and I start them near this red curve, as I evolve the system further in time, those curves move out and out and out along those green directions. Okay? And what that means is that with a very small amount of input to my system of control, if I'm near a saddle, I can go really, really far in either direction. I get a lot of possible outputs for a very small change in my input. Okay? Good. I'll talk a little bit more about this. Yes?
So Maxwell already, he envisioned chaos as a separation by saddle points. He thought that the complex system must have a lot of saddle points, which act kind of as a flipper where you go right or left.
And I mean, to some extent, that is how our solar system works. That's how turbulence works. There's a lot of important saddle points, and I'm going to talk a lot more about these. Okay, I just wanted to point out this is what I'm talking about when I say a saddle. Okay, good. How many of you have heard of bifurcations? Good, perfect. So I'll go pretty briefly through this. Bifurcations basically means if I have some parameter in my system, this mu, sometimes I call it beta, I can get very, very different behavior as that parameter changes. So for example, in this case, I can write this system as x times mu minus x squared. How many fixed points are there in the system? It's the trick questions. I hear some of you saying 3, some of you saying depends, some of you, right? So if mu is negative, then there's only one real solution. I'm assuming that x is a real variable, okay? So if mu is negative, then there's only one solution, fixed point at x equals 0. But when mu becomes positive, 2 new fixed points appear at plus or minus square root of mu. So that alone is interesting, that depending on mu, I have a different number of fixed points. Okay, that's kind of what a bifurcation is. And so if I look at my Jacobian, my derivative of these dynamics with respect to x, I get mu minus 3x x bar. This is my fixed point squared. And so at these 3 fixed points, I get completely different dynamics. Okay, the x equals 0 fixed point and the x plus or minus root mu fixed points have the opposite sign dynamics. So one of them is stable, the other one is unstable. Okay, and that's what this bifurcation diagram, this pitchfork bifurcation shows. The x-axis here is increasing mu, and the y-axis are essentially the fixed points x. So for negative mu, I only have one fixed point and it's stable. These blue arrows mean it's stable. I have one fixed point at x equals 0 for negative mu. And the instant mu becomes positive, that fixed point goes unstable. I think this should be, this is positive mu, so it's unstable. Okay. And immediately I get these 2 branches of solutions, these new fixed points that are themselves stable with these eigenvalues minus 2 mu. So this is what we mean by a bifurcation, is that as you vary your parameters, you get these drastic changes. So everything is the same, and then your whole world changes at a fixed value of mu. And this is something we need to worry about, right? Like the global food supply, populations, disease might have bifurcations where we're just merrily going along, and then at some point we crank something up too high and everything breaks. Okay, this would be a lot worse if this bent the other way. Okay, that's a different type of bifurcation. In fluids, we talk a lot about Hopf bifurcations. So I think you've already seen these before, and you're going to see more of these. So for example, in the fluid flow past a cylinder example, as you increase the flow velocity or the Reynolds number, you go through this Hopf bifurcation, where your steady flow pattern becomes unsteady at some critical Reynolds number, and then you get this periodic vortex shedding limit cycle. And if you had a sequence of Hopf bifurcations, you could eventually build a route to turbulence. Okay, that's the Ruel-Takens route to turbulence. And so this is the kind of normal form that you would get for a Hopf bifurcation in my 2 variables, x and y. Again, where mu is the thing that I'm increasing or decreasing to get this periodic behavior. Okay, and what I think is really interesting here is that if you write this in polar coordinates, and this is a good homework for you, you could probably do this on a napkin, is just write this in polar coordinates. You recover essentially your pitchfork bifurcation here. Okay, so I mean, and no wonder these look pretty similar. Okay, good. You can also have discrete time dynamical systems. So everything I've talked about so far is for continuous time, the time derivative of x equals f of x. But I could also have discrete time dynamical systems that step forward in time discretely. Okay, and so this is one of my favorites, the logistic equation. So x at time step k plus 1 equals mu xk times 1 minus xk. Okay. What would be some systems that are fundamentally discrete time in nature? I always think about my bunny population in Seattle. There are seasons. Okay, it's not exactly a continuous time system. There's, I have a bunny population in spring of 2019, and then I have a bunny population in spring of 2020 and 2021. And actually that is what this equation is modeling, is essentially population dynamics, okay? Anyway, you can also write down discrete time dynamical systems. That's something that we do a lot. Okay, would anyone like to ask any questions about anything I've talked about so far? Good. Okay, we're going to just build up complexity here. So I've talked about linear systems, weakly nonlinear systems where we linearize and look at phase portraits and stable and unstable manifolds and bifurcations. Now we're going to talk about chaotic dynamical systems. This is a video I made for my undergrad class to show them what chaos means to some extent. And there's a lot of different definitions of chaos. I think it's really fun and interesting. The definition that I think is most useful is a sensitive dependence on initial conditions. Okay, so if I started with two initial conditions that are very close to each other, and I integrate them through a chaotic system, so that cube started with really close initial conditions. And those initial conditions stay close to each other. This is the Lorentz system, by the way. They stay close to each other for a long time until eventually they don't. Then they start to spread and smear out on this attractor. And if I just showed you a picture, at time now, you wouldn't know where all of these initial conditions came from. You wouldn't be able to tell which one was which one. Okay, so a small cube of uncertainty can amplify a lot in these chaotic systems. The Lorentz system is really interesting. It's essentially a three-state model to model convection, atmospheric convection. That's where Lorentz was trying to model. And he actually, you should go back and read this paper. My friend John Christophe Loiseau convinced me to go back and actually look at this paper, because Lorentz derives this using Galerkin projection onto hand-picked modes. So it's very relevant to what we're talking about today in this workshop. This is essentially a hand-tuned Galerkin model for Rayleigh-Benard convection. Okay? But this is what I mean by uncertainty growing in chaos. Okay? Another example I like to show in my class is this one here. So these are my double pendula that I built in my lab. I'm not an experimentalist, but this is about the best thing I can build. It's double pendula. Cardi, you'll see later, built some really nice ones. Okay, is this going to run again? So notice that I started them with the same initial condition. They were at that right angle initial condition. And they actually stayed together for a really long time. That was like my best initial condition I could get. I held my breath. It's pretty impressive. They stay together, and then they don't. Okay? Because small variations in the friction, the weight, all of those things eventually amplify into this kind of large growth over time. Okay? Now, what is the hallmark feature of a chaotic system and this increase in uncertainty in time? What's my favorite feature of a nonlinear dynamical system?
The positive Lyapunov exponent?
Let's call, an unstable direction.
Okay.
I would call it an unstable direction. You need some instability. Okay, instability is one of our best friends for control. Fighter jets, the things we want to control the fastest, are designed to be unstable until you wrap control around them because they turn faster. A human walker, saddle points, right? I need saddle points for chaos, because saddle points are going to have that unstable direction that I need to grow exponentially my uncertainty in forward time. Remember this picture here? This dynamical system exponentially grows uncertainty in the green direction. That exponentially grows in forward time. And that's exactly what chaos means, is this exponential growth of uncertainty in forward time. So somehow saddle points are important. The reason I study this pendulum system is because this has a very special type of saddle point called a rank 1 saddle. Okay, so I'm actually going to talk about this a little bit longer than I was planning on, because pendula are super fun. So I can actually pretend that my arm is a double pendulum. Okay, this is the big pendulum, this is the little pendulum. Okay, and the system has how many fixed points? How many? Not 2? 4? 4 sounds good. So I could have down, down. Yeah, that's a fixed point. I could have down, I can't do this. Down, up. That's technically a fixed point. It's unstable, right? Because if I push this one, it's going to go. I could have up, down, also unstable, or I could have up, up. It's 4 fixed points. Okay. Now the down, down is stable. Right? If I looked at the eigenvalues of this, I'd have like plus or minus I omega and plus or minus another I omega. It would just oscillate with 2 frequencies. But the down up and the up down are what are called rank 1 saddles. They're only saddles in one of the directions. So I don't know which one I should use, but in this configuration, the big pendulum is stable. That has eigenvalues plus or minus I omega. But the little pendulum is unstable. It has eigenvalues plus or minus real numbers. It's a saddle point, okay? And these rank 1 saddle points are really, really, really important for efficient control and transport. As a human walker, I'm a multi-jointed pendulum, right? I've got my ankles, my knees, and my hips. So I'm like at least a 3-jointed pendulum. And that's a really good thing because I'm always constantly almost unstable. This is when I would normally wake up in Seattle, by the way. If you shot lidocaine into my ankles, I would fall over because I am a fundamentally unstable inverted pendulum until I actively control. And what's nice about that is that it means that I can very efficiently propel myself with almost no control input. All I have to do, right, I'm an unstable pendulum, I just go a little bit and I go a long way. I push myself a little bit off of equilibrium and the instability carries me almost for free in the direction I want to go in. Okay? It's an extremely good thing. Like, we are very efficient because we're unstable. Fighter jets are really, really easy to turn because they're unstable. And so these rank 1 saddles offer us the opportunity to control my system very effectively. So chaos, again, it's a challenge, but it's also an opportunity. Systems that are highly unstable can be manipulated easily. This is my favorite example of this. This is what Jerry Marsden and others were working on at Caltech in the late 90s that I think is super interesting, is using these saddle points for space mission design. Okay, so I'm going to walk you through this example. You have, let's say, the Sun and Jupiter. For all intents and purposes, those are the ones that matter in our solar system. Whether we like it or not, they're the big ones. And in the Sun-Jupiter system, there are 5 fixed points, these Lagrange points, L1, L2, L3, L4, L5. And I'm only going to talk about a couple. I'm only going to talk about L1 and L2. But L1 is clearly a saddle point. It's clearly unstable. It's the equal gravity point. Because if I was hanging out there at L1 just floating there, and you pushed me a little bit towards the sun, now I'm closer to the sun, and I'm going to accelerate towards the sun, right? And if you push me a little bit towards Jupiter, now Jupiter is more influential, I'm going to accelerate toward, it's an unstable saddle point. And it's one of these rank 1 saddle points. That's really interesting. It has 2 stable directions and 1 saddle direction. L2 is similarly a rank 1 saddle. And I don't know, it's a little hard to see these level sets here, but these level sets are essentially outlining what regions are permissible if you were an asteroid or a meteor traveling with a certain amount of energy. Okay, so if I have a low amount of energy, I would basically bounce off of that energy level set. And the only way I could get into the inner solar system is by going through L2, then around L1, and then into the inner solar system. And so to some extent, Jupiter is protecting us from space junk outside of Jupiter. It is providing these barriers, these energetic barriers protecting the inner solar system. And so the only stuff that can come in or out with moderate energy is coming in and out through these saddle points. Those are the mediators. They're like the turning revolving doors for our solar system. And it's really interesting. During this time period, they discovered that some freakishly large number of asteroids in our near vicinity are in binary orbits with each other, which you would never expect, right? Space is so large and they are so rare, you would never expect asteroids to be orbiting each other. But something like 5 or 10% of our near Earth pairs are actually paired up. And the thought process is that because the only way they can come in is through these saddle points, that they had to have paired up as they entered the saddle points together. Very interesting. So it's essentially organizing the material in and out of the inner solar system. Yes?